Hi everybody, and welcome to 5 design patterns to build resilient applications. My name is Derek Bingham. I'm a developer advocate at AWS, and over the next 40 minutes I'm going to show you 5 patterns and a practice that you can use to make sure that the next cloud native distributed application that you build is more resilient and delights its users. So I'm going to start with a quote from the Amazon CTO, Dr. Werner Vogels. Failures are a given and everything will eventually fail over time. So this is nothing to actually be afraid of. It's actually saying that when you're building modern cloud native distributed applications, they use many different components across networks, across hardware stacks, across software stacks, and it's a fair chance that some of those components may fail, and in fact will fail. And as a software developer and building those modern cloud native distributed applications, we need to think about this failure and those failure modes so that when we're building our software, we can take them into account and as a result, make our software more resilient and delighting our users. So today, I'm going to show you how to do that by taking you through 5 patterns and a practice that you could use when you build your next cloud native software application. The patterns I'm going to talk about are timeouts, graceful degradation, retries, exponential backoffs, and circuit breakers. And the practice I'm going to talk about is chaos engineering. So to start with, I'm going to introduce you to the application we're going to build. It's going to be a traditional distributed application. I'm going to change this application as part of this talk to make it more resilient using these patterns. So let's dive in. If I have a look at the application itself, you can see that up in the top left, I'm going to scroll there. We've got a React app inside the client app folder. And inside that source directory, I have got a component directory, and inside that, a fetch data.js. So this is the main component of my React app. So the fetch data.js has got a constructor, it's got a table in it that renders jokes, more on jokes in a second. And if you scroll down a little bit more, you'll see there's a button and some contents. But the really important function is this, populate joke data. You'll see that the function ultimately calls an API/joke endpoint, gets some response in JSON, and then renders that response. So that is the React app. Also, we have an API. So this is what the React app is hitting. It's a .NET controller. It defines a joke client. And in the joke client is, if we have a look at it now, defines a joke URL. So this is a third-party joke API that this client calls. And in here, we've got an HTTP client, which is how .NET does REST calls. It hits the joke API, gets a response in JSON, and then serializes that JSON back out to the React app. Now, the serialized JSON, this is the object that it's serializing. It's got a joke, and it's got setup, punchline, and source. And we'll go more into that in a second. So this is the app running. So this is my little React app. Why are monkeys great at sports? They're born champions. If I hit refresh, it'll give me another joke. What's the object-oriented way to become wealthy? Inheritance, of course. And then finally, how many programmers does it take to change a light bulb? None. It's a hardware problem. As well as the UI, here's my API. So I'm showing you what the little joke client is hitting, and comes back with the joke as part of a setup, the punchline, and the source. Currently, the source is always going to be third-party API because that is what I'm hitting. So the architecture of this application is the React web app makes a call to the .NET microservice, which then proxies that call into the third-party joke API. Simple. The third-party joke API returns a response to the microservice, which then proxies it back to the React web application, which renders the joke and the punchline. But what happens if the third-party joke API starts to have a problem, starts to have a component failure? what would happen? Well, our React web application doesn't know about this, so it will continue to make requests. The .NET microservice will continue to proxy, and it may actually then start waiting for the response. Third-party Joke API is under load, it could be failing, so it may not be able to return a response. And then the .NET microservice, as a result, won't be able to return a response to the React web application. So if we had another React web application from a different client or a different browser, it would do the same thing. The .NET microservice would proxy it through the third-party Joke API, which would then wait for a response, as the third-party Joke API is still with a component failure. And then React web application would also have a delay. And what would happen eventually after a number of requests coming through .NET microservice is the .NET microservice would actually continue, might overload and might itself have a component failure. And the React application would continue to request and continue to have a very bad day for its users. So as you can see, this is one thing that we want to emphasize is we want to have our users to be as delighted with our application as possible. So let's see how we can do that by implementing pattern 1, which is timeouts. The first thing I need to do is I need to add a timeout to the HTTP client. I do this in .NET by just adding a property to the HTTP client, and the property in this case is called timeout. So the timeout itself, I can set for a time span. For this one, it makes sense to go a time span not of 0, but of seconds. And for this, I'll probably set a time span of 5 seconds. So what this is doing, it's basically saying that for this client, then have a timeout after 5 seconds. So if I do a request, how many programmers to try to change a light bulb? If I hit that request, if the request takes longer than 5 seconds, it will time out. So here it didn't take longer than 5, so I got a response back from a third-party API. If I do it again, loading, it may take more than 5 seconds this time. It has. So the UI is actually frozen as it waits for a response. But then if I see what's happening in my .NET microservice, if I do a refresh a couple of times, it's coming back from a third-party API, okay. But then, boof, what I get is a timeout exception. So what's happened here is my .NET microservice is requested my third-party joke, and after 5 seconds, it's timed out. So that is how to implement timeouts. So as you can see, that's a way of stopping that .NET microservice from waiting on the third-party Joke API for a minute, which is the default HTTP timeout. You can actually reduce that to 5 seconds and then handle that timeout exception and return an error to the client. However, or retry again. However, it's not very granular, that timeout. So how can we make that timeout a bit more granular, i.e., in different parts of the request the client sends to the third-party Joke API, we can put timeouts in that. So that's how I'm going to talk about pattern 1A, which is improving timeouts, how to make those timeouts more granular and give you more control to make sure that your application is resilient and behaves. So this time I'm going to get rid of the original, I'll call it the simple timeout, put the client code back to the way it was. And for this one, I'm going to start using a library, the .NET library called Poly. So Poly is a resiliency library that we can use. So every language out there will have a resilience library. Poly is just the one for .NET. There's a resiliency for J if you want to use Java, and other languages have a similar library. So in Poly, I'm going to set a timeout, an asynchronous timeout of, again, 5 seconds. But now I'm going to wrap my request and response code in an anonymous inner function. So if I go policy dot execute async, and then inside that I'm going to have an anonymous async function, which is going to have a cancellation token. So CT, I'm going to define as my cancellation token. So what it's doing is I can cancel individual tasks inside this anonymous function. So all I'm doing now is pulling that code up into my function, like so, and just finish up the indenting here. And so now this function is going to execute, but I need to define my cancellation token that will give me the control over async tasks within this function. So get async can have a CT, a cancellation token, as can the response. So I can control that cancellation token and give you a bit more granularity of control inside that timeout. If I go back and rerun this application, you'll see what that looked like. So back inside my joke app API, once it spins up, you will see that why are monkeys great at sports? They are definitely born champions. Tell me another, and refresh. Oh, came back within 5. Refresh again. On we go back, and let's just refresh this. Refresh. They're all coming back really quickly now. I was away. So my third-party API, which you remember I put in a random delay in, and here we go. It's greater than 5 seconds, so we get this delegate executed asynchronously throughout the timeout policy. So it did not complete within the timeout. So again, the exception isn't caught because I'm demonstrating it here, but it gives you a better granularity of control over the timeout. So the next pattern we're going to talk about, now we've talked about timeouts and how we can improve timeouts by making them more granular, is another addition to timeouts, and it's called Graceful Degradation. Now, with our previous timeouts, we had thrown an exception and expected the client or the .NET microservice to handle that exception and do something. Well, the Graceful Degradation is the do something. So it is, when you're calling a third-party API, you want it to return a response to the client or whatever is calling it in your system so that it thinks that it's still working. So it's degrading gracefully. And we implement that in our applications, again, to delight our users. So let's see how we can implement Graceful Degradation in our application. So let's build out what Graceful Degradation will look like using the poly library. So from poly, the next thing I need to do is I'm going to define a fallback policy. So what a fallback policy is the policy that poly will call if my original policy throws an exception. So this fallback policy will return me a list of jokes. So IEnumerable is a list of jokes. And what it has to do is it has to handle a type of exception. So I'm going to be very generic here and say handle exception, well, generic exception. Once I've defined the exception it's going to handle, the next thing I will need to do is say, okay, what am I going to do when I fall back? So this is the fallback async method that I'm going to define. Again, this takes an enumerable, so a list. I'm just going to tidy this up so you can see it. Next line. Again, this takes an enumerable of jokes. And inside the fallback async, I'm going to do another anonymous function. And inside this anonymous function, I'm going to return a joke or a fallback joke. So what this is doing is, again, async the cancellation token into anonymous function, enter new list of jokes. And for this list, I'm going to, for the sake of everybody watching my typing, only have one joke to be returned. And so if you remember, my joke object has a punchline. It also has a setup and it has a source. So we'll define those inside my joke object. Setup is a string. Punchline is also a string. And then source is a string, consistent. So let's think of a joke, another marvelous joke. So let's have a band joke. So I'm in a band. It's called 123 megabytes. We haven't, triple punctuation, had a gig yet. Now the source is going to be fallback. So this is going to show us when in the UI when we have hit the fallback. So next thing I need to do is I need to pass that policy into a wrapper. So the policy wrapper is how I can pass different policies, almost chain them in an order of precedence. So what I'm going to wrap async is the fallback policy, which I've done there. Then inside that, I will wrap the policy. And so now, once the policy fails and throws an exception, we should then get the fallback policy. And the last thing I'm doing, I need to pass the policy wrapper to the execute async. So once that is done, we are going to gracefully degrade the API, so the endpoint. So let's refresh the page. What's two hard things about computer science? Cast and validation, write things, and that. We refresh again. And we're waiting for 5 seconds. Oh, here we go, fallback. So I'm in a band called 1023. We haven't had any gigs yet, and that's the source of fallback. Refreshing the backend to see what happens in the API calls. Again, and there we go. We're coming to fallback. So as you can see, we refresh. If we hit more than 5 seconds, we show the fallback. If we hit again, the API is working, we get a normal response. If we refresh again, we may then get the fallback if it's over 5 seconds. So what it's doing is over time, if the API is having problems, we gracefully degrade it. Okay, so the next pattern we're going to talk about is retries. So retries, again, is a simple pattern to implement. And it's all about if a particular event happens when we're calling an API, could be a timeout, could be a fallback, then we retry it, and we retry it a number of times in a particular time frame. So let's see how we can implement that. So the next side, I've just changed the timeout to be 2 seconds, not 5. Otherwise, we could be waiting here for a while. And what I'm going to do now is define a retry policy. So the retry policy is, again, another policy. This time, the handle is, again, going to be in exception. And on exception, you define what your retry async method is going to look like. So remember, the last one was a fallback async. This one is a retry async. So we're going to set a retry count, which is a 5. And once the retry count is set, we're going to add that policy to our policy wrapper. So remember, it's a concatenation of all our different policies. So what we're saying here is if the original policy doesn't work, do a retry of that policy. If that doesn't work 5 times, then hit our fallback policy. So that's what that policy wrapper is doing. So let's see what that looks like in our app. So let's restart our app. Starting our app up. And so let's refresh. Thinking, loading. So I tell you, UDP joke, you might not just get it. These jokes are great. How many programs does it take to change a light bulb? It's a hardware problem. Tell me another. So far the API is behaving. So now it's loading. Remember, we're hitting that API. If it doesn't respond, Then we're going to do retries up to 5 seconds, up to 5 times. And if that doesn't get back to us, we should then retry, get our fallback. So here we're loading again, we're retrying, Remember, they'll time out, each request will time out after 5 seconds. And here we are, we're in fallback. So what's happened is the API has been hit 5 times. It's timed out, every timeout has been 2 seconds. So 10 seconds in total. And if that didn't work, we hit our fallback. So that's the retry pattern. So with the retry pattern, we can have more granularity over our retries, over our timeout. But again, we always have that graceful degradation, that fallback in place. Okay, so that's retries. Now, the next pattern is an advancement of retries. It is called exponential backoff. So with exponential backoff, it is solving a problem that can happen with retries. What is that problem? Well, when you have a client and it makes a request to the .NET microservice, which then proxies it to our third-party API, and the third-party is suffering a component failure, we will ultimately time out. And then after a period, we will start to wait and retry after 2 seconds. But what inevitably happens is, what if everybody is retrying after 2 seconds? Well, what's going to happen is the third-party API will come under load as the clients keep retrying every 2 seconds. So what exponential backoff does, it backs off that retry exponentially. So the next retry actually doesn't happen after 2 seconds, happens after 4 seconds. And then the next retry after that, if the third-party API doesn't return, happens after 8 seconds, and so on, until we get a response from the third-party API, or we decide to implement our fallback and return a response to the client. So let's see how we can implement a exponential backoff in code. So here we are back in our retry policy. So exponential backoff is simply changing this retry policy and adding that math factor to it. So what we want to do is apply a wait and retry async, and then define the wait mathematics, if want of a better word. So what we're going to do is we're going to rate, which we're going to try 3 times, and then each retry attempt we're going to do over a particular time span. So that time span, we're going to have a seconds math par. So we want an exponential. So what we're going to do is a math par of 2, and then retry attempt again. So it's going to give us that 2, 4, 8, 16 time frame that we looked at in the slides. If I just tidy up the retry attempt, I can spell. There we go. That should do that, and that is our new retry policy. Just tidy up the code, save it, and see what this looks like. Rerun the client application and see what the exponential backoff looks like. So refresh. So as you see, we're loading. We are calling it. We time out after 2. We'll retry after 2 seconds. Time out after 2. We'll retry after 4 seconds. All the way up into 14 seconds. And then if we hit 14 seconds without a successful request, we will get this, which is the fallback. But as we retry, we should then get successes as well. So let's wait for that. It could be bit. We're retrying. We're waiting for 2 seconds. Retrying. Waiting for 4 seconds. Retrying. And there's one. There's only 2 hard things in computer science. And then there's our world's joke. We're not werewolves. What if exponential backoff is not enough? So, as I explained before, purpose of exponential backoff is to try and give the third-party API or a component in your system a chance to recover. And we do that by adding a time frame between each retry. But what actually happens is everybody and all clients end up using the same numbers for retrying and for their exponential back off. So what happens is it clusters anyway. And so you can see in the graph on the left here, you actually create a distributed denial of service on your backend server. So you really want that load to be distributed more equally. So that's why we add jitter, which is a random number between retries instead of the exponential backoff pattern that we saw before. So let's see how we would add that exponential backoff with jitter in code. So if we go back into my wait and retry async, I need to improve this to add in that randomness. So I do this by adding a time span of millis, and it's a new random, and it's going to be between 0 and 1,000. So 0 and 1,000 millis. So it's going to give us a plus or minus 1 second randomness towards our retries, and that's it really. And that's all we need to do, because if you think about it, then we're less clustering because it's purely a random retry. And that's it. The next pattern we're going to try is the circuit breaker pattern. It's a slight evolution of a fallback mechanism. So let's see how that works. So with a circuit breaker, it falls back after a certain threshold is released. So how does it determine that threshold? Well, as we can see, the React web application, again, makes a request to the .NET Service proxies to a third-party API, which has a component failure. The .NET microservice, every time it requests it, it'll retry and retry, as we've shown before. Now, what we do with a circuit breaker is after a number of retries, or a threshold, we implement a circuit breaker. So the circuit breaker will last for a number of minutes, so that when the next request comes through from the .NET microservice, it will not be then proxied to the third-party joke API, but instead it'll invoke the circuit breaker, which will return a response and enable the .NET microservice, in our case, to get that response back to the client. And that circuit breaker will stay in place and return responses to the client for as long as we specify. So let's see what it looks like in code. So the circuit breaker itself, we're going to define as another policy. So first of all, we define the circuit breaker policy, and we're also going to define a circuit breaker fallback. So we can tell the user when the circuit breaker has actually been evoked. So first we do the circuit breaker policy. Again, we have called policy. For the circuit breaker, again, we're going to handle an exception for any general error that happens. And then what's going to happen when this exception occurs? We're going to define a circuit breaker. Just tidy this up a bit, just indent it a bit so you can see it. So the circuit breaker itself, we're going to say if they call the API 5 times, in a minute, it's going to break that circuit for 1 minute. So if you call the API, it has 5 exceptions, then we're going to implement the circuit breaker for 1 minute. And then how are we going to know that a circuit breaker is in place? Well, we're going to implement a circuit breaker fallback. And this is what we're doing now. So circuit breaker fallback equals policy. So the handler for this policy, the fallback is obviously, like all our other fallbacks, is going to return a list of jokes, which is going to be 1 joke. But it's going to handle, and this is a little bit different, we're going to handle a circuit breaker exception. So it's only going to be invoked when we get a circuit, when the circuit breaker fails. So let's write that. So handle circuit breaker exception, which is called broken circuit. And then once that appears, let's then do our fallback. And inside our fallback, again, we're going to have another anonymous inner function returns the jokes. That is our fallback joke. So I get to think of another joke, which is exciting. So this is exactly like the other fallbacks where we have an anonymous inner function that simply returns a list. That list is a single joke. Oh, that's over there. I need to tidy that up a bit, indent it. There we go. And let's define the joke. New joke. Inside the joke, we need a setup, string, setup, punchline, also string, and then our source. So this will be from our circuit breaker. With single K, thank you. So another joke. Oh, alrighty. So why did the developer go broke? Well, obviously it's something to do with cache. Because they used up all their cache. Kaboom tish. Just make sure I've got all the looking all right. Tidy it up a bit. Yep. So and finally, of course, we add this into our wrapper. So concatenate in our circuit breaker and our circuit breaker fallback. Okay, so once that's in, we can save and we can redeploy and run it in our client app. And hopefully we will get to our circuit breaker fallback and see how the circuit breaker actually works. So if we redeploy it, wait a couple of seconds, get back into our application and hit the refresh. Oh, that was very quick. So the API works first time, of course, there. We're hitting loading. We're retrying. Remember, we have to retry 5 times before the circuit breaker comes in. So that wasn't 5 times. No. Try another. Nope. Of course, it's always the way when you're trying to test a particular use case. Oh, this is a bit more. This looks like we're trying to retry 5 times. Exceptions. We need 5 exceptions, and then our circuit breaker is going to come into force. This looks good. No, oh, this is it. Yep. So source circuit breaker fallback. And so now if we invoke the API, we should then get our circuit breaker right away because it's not going to the third API. It's not going to get any exceptions from that API or retry that API. It's just going to go directly from our circuit breaker. So that's the power of a circuit breaker. And then after a minute, of course, it will go away and we'll start hitting our API endpoint again. So that's how they implement a circuit breaker. And that, in fact, is all of the patterns that we're going to discuss today. What we're going to discuss now is the practice of chaos engineering. So what is chaos engineering? So as we've seen with our demonstrations and our patterns, the third-party joke API would go down randomly. So how we do that is by applying the practice of chaos engineering, where we stress the system, we observe what happens. So in our case, we stressed the third-party API and we brought it down randomly. We observed what happened, and then we improved it by building the patterns that we've had through the rest of this talk. And so what does that do? Well, it helps you improve the resilience of the application, obviously, and also its performance, because as you can see, as we made those improvements using the pattern, the client application became more responsive and performant. It uncovers hidden issues. So we had a number of issues with our .NET microservice that we worked through and improved. Exposes blind spots. So sometimes when you're using an application, you always look at the happy path, and sometimes you don't actually consider what could go wrong. And so chaos engineering, by injecting those failures, helps you to consider that and make your code more resilient as a result. So I'm going to take you through now one of the AWS services that helps you inject chaos into your system, called the AWS Fault Injection Simulator. So I'm going to give you a quick demo of how you would use that fault injection simulator with a third-party API. So let's say that the third-party API we've been using, the joke API, is running across a suite of EC2 instances. Let's see what we would do to inject chaos using the fault injection simulator. So we talk about experiments. When we're talking about chaos engineering, when you inject experiments into our running application. So this experiment, we're going to stop instances. Now, just to reiterate, everything I do here actually stops the instances. It actually works on real services. So this is not a mock or anything. This will actually happen. So disclaimer there. So we call an action called stop instances. Inside that, we give it a target. And inside the target, we give it some parameters. So we're saying that for all of the instances, we're going to stop them for 1 minute. Once we've defined the target, we next need to say if there's any tags. So all of my API servers, EC2 instances, I've tagged with EC2. Oh, sorry, with API. So that way I can be very targeted in what I want to do with this experiment. Once I have defined the experiment, I can create it. And once it's created, you can see that these are my API EC2s, and they're all running. I can then run my experiment. So I start my experiment. You get lots of warnings because this, as I say, this is real. This is really happening. And the experiment will start to run. So as you can see, the experiment now is pending. The EC2s will run, but if I keep refresh, we should see them stop. So see, this is the experiment. And now it's running. So there we go. So all the instances have now stopped, and they will stop for 1 minute because that's what I've defined my experiment. So then I can build my application and test my application to see how it's handling the issue of having no servers there. So as well as stop instances, there's all swathe of actions you can use with the fault injection simulator. Where you can, if you're using containers, you can drain container instances. You can do a lot of different actions with the fault injection simulator, not just the very simplistic action of stopping a server, which I'm doing. So this is back inside our app. So we've waited a minute. If we then refresh, there we go, our instances are back up. So that's showing us that how targeted the fault injection simulator can be, quite granular. You can define time spans that you want the chaos to actually exist in. So if you want to test this in production, you might particularly test specific services for a specific time frame at a specific time of day. So that's cool. So that's it. Thanks for listening until the end. I hope you've learned something today. One of the patterns you may not have come across before, or the practice of chaos engineering. And I hope my explanation did them justice. Thanks for listening and making it to the end. My name is Derek. I'm a developer advocate at AWS. If you have any questions about today and any of the topics that I mentioned, you can always reach out on Twitter. This is my handle. Thanks again for listening, and I'll see you next time. Bye.